Good morning. Good morning. We are going to polish off our topic on molecular shape. So we've reviewed Lewis structures, Vesper structures. We can do bond angles. We know how molecules look in 3 dimensions. We know bond. We've done bond polarities. Here, kitty, kitty. My cat's being weird. So let's put all of that together. Really, this whole thing, electronegativity, bonds, bond polarity, shapes, Lewis structures, all of it was just to answer one simple question. If you have a molecule, is that molecule polar or nonpolar? That is such a key thing to be able to answer. If you move on in chemistry or go apply it and make money with it out in the real world through a job, or maybe you run your own business or something like that, if you're creating some medicines and drugs and things like that, one of the first things you want to ask is this polar or nonpolar? I.e., for like a medicine or drug, is it water soluble or fat soluble, right? That's important. Those types of questions will be answered by determining molecular polarity, right? It's a huge, if you go into organic chemistry or biochemistry, physiology, this is going to be a huge thing, because how does a particular species or molecule function in your body? If it gets into your bloodstream, or if it encounters another molecule or species, how does it react? Molecular polarity is going to be a huge factor in the reactivity. Like I said, determine solubility. We're going to find out that it has a huge impact on its melting points and boiling points, specific heats. Holy moly, right? A huge factor of incredibly important molecular properties and reactivities determine on answering this one question. But it's more than just say, is it polar or nonpolar? Well, yes or no. You can guess with a 50% chance. You'll never get that on my exams. You have to show why. You have to go through, do the Lewis structure, do the Vesper structure, look at its three-dimensional shape, look at its electron distribution. How are those electrons distributed amongst the atoms of that molecule? There's a lot to it. Seems like a simple question. Going to take a while to answer. So we looked at bond polarity, and we just looked at the bonding electrons, whether it's 2, 4, or 6 electrons, single, double, or triple bond. Doesn't matter. They're stuck in that locale in between the two atoms, and we just looked at the electronegativity difference between the two, right? So a little closer to this one, a little closer to that one, can create partial charges and a bond dipole, right? With a dipole moment, we used an arrow pointing towards the partially negative side. We can do the exact same thing for a molecule. It's just a molecule is a sum of multiple bonds. Right? A molecule has 2 or more bonds, right? And there might be lone pairs on the central atom, et cetera, et cetera. We're going to focus on simple molecules first, and then we can look at complex molecules. But in essence, it's just the electron charge distribution over the entire species, the whole molecule, or how is the electron density over the whole molecule? Are there more electrons? Is there a higher electron density on this side than that side, et cetera? We can figure that out. Obviously, if one side has more electron density than the other, it has more of a negative charge on that side than the other one. So if it's a symmetric electron distribution, so if we went around that whole molecule with our little fictitious, like our electrostatic potential mass with our little, fairy wand with a positive point, we look around and your charge wand would be like, well, it's exactly the same everywhere I look. Everywhere you go, it has the exact same electron density. Well, that's perfectly symmetric. We would call that a nonpolar molecule. So another molecule coming in to react with it would be, maybe it's looking for a negative side. It's go, oh, well, I don't sense any side around here to react with because it's a completely neutral molecule. There's no side that's more negative than the other side. But if it's an asymmetric or not symmetric electron charge distribution, or the electron density is higher on one side than the other, the side with more electrons, or a higher electron density, usually the side with more electronegative atoms, but we got to look at shape, will have a higher negative electron charge buildup, and that will build up a partial negative charge, right? So, and then the other side has less electron density, that builds up a partial positive charge. So one side of the molecule is partial negative, one side of the molecule is partial positive. That's an asymmetric or non-symmetric electron charge distribution. That creates a polar molecule. It has 2 poles, negative pole or partial negative pole, and a partial positive pole. There you go. That's it. We use a little arrow to represent it, just like we did with bond polarity, but we just kind of shish kebab the molecule through the central atom, go whoosh, right? For simple molecules, complex ones are a little harder to do. So we got one partial negative side, one partial positive side. That creates a dipole moment of the overall species. You can have bond dipole moments and you can have molecular dipole moments. So one thing I want you to get in the habit of is whenever you say polar or nonpolar, I always want you to say, is that a polar bond or is that a polar molecule? Is that a nonpolar bond or is that a nonpolar molecule? Because a polar molecule is the sum of its bond polarities. So you need to be super clear on whether you're talking about an individual bond or a molecule, which is a conglomeration of bonds. Oh, let's look at this in more detail. All right, molecular polarity seems simple. It's only based on two things, but each of those is based on other stuff. So two factors. So when I ask you a question on test, hey, is this molecule polar or nonpolar? You want to start out by going, hey, what kind of bonds does it have, and are they polar bonds, right? Are they nonpolar covalent bonds, polar covalent bonds, or ionic bonds? But we're going to be doing molecules, so we won't get ionic bonds. And remember, in real life, bonds are actually partially ionic, partially covalent, but we're going to simplify it and just say, hey, is that a polar bond, delta En greater than 0.4, or is that a nonpolar bond, delta En equal to or less than 0.4? Simple, right? Just do that real quick. And you got to do that for every single bond that's in the molecule, right? So it might have 3 polar bonds and 2 nonpolar bonds, or all 4 nonpolar bonds, or all 4 polar bonds. Right? You got to look at each one. So the bigger the molecule, the more work you got to do. And then secondly, symmetry. So bond polarities and symmetry. So look at whether the bonds are polar or nonpolar, and then we have to look at how those bonds are arranged in three-dimensional space. Are they arranged symmetrically? Are they arranged asymmetrically? So we're interested in looking at, is the electron density symmetrically arranged or asymmetrically arranged throughout the molecule? And we got to look at the bonds and the symmetry. So symmetry, of course, is based on Vesper structures, which is based on Lewis structures. So you got to draw the Lewis structure, and that tells you what kind of bonds you have. From the Lewis structure, you draw the Vesper structure with the dash wedge model. And then from that, you get the molecular geometry and all the bond angles, and then you can tell, well, that's symmetrically arranged or asymmetrically arranged. Let's peel off another layer of the onion and look a little bit deeper, and then we'll do some examples. Here's how you can think about it in a little bit more detail. I got a molecule and I want to know, hey, is this polar or nonpolar? Okay, remember we got to look at the bond polarities and the Vesper structures, which leads us to symmetry. So really it's symmetry and electron charge distribution through the bond dipoles. So to be a nonpolar molecule, we'll look at polar molecules next. To be a nonpolar molecule, I think it's easier to see if something's nonpolar. You can go, hey, it has all nonpolar bonds. Wouldn't that make sense? If all the bonds are nonpolar, how could the molecule be polar? That's typically 99% of the cases. There is an exception to that. You could have all nonpolar bonds, but if you've got a lone pair on the central atom, usually through some expanded octet or something like that, and it distorts the symmetry. So now you've got these nonpolar bonds, but it's asymmetrically oriented because of these lone pairs on the central atom. That can create a slightly polar molecule, and kind of an exception to the trend we'll run into. But typically, if you have all nonpolar bonds, it's going to be a nonpolar molecule because the electron charge distribution is the same everywhere. Or it has perfect symmetry. Maybe you have polar bonds, but if those polar bonds are symmetrically oriented in three-dimensional space, and they all have the same dipole moment, that means the electron charge distribution is exactly the same. The electron density is exactly the same everywhere, even though it has polar bonds. But if it's symmetric, which you determine from the Vesper structure, all those bond dipoles would cancel out in 3 dimensions, and you'd have a nonpolar molecule. Cool. And you can usually see from a model or just in your head, that's symmetric, right? Let's look at what makes something a polar molecule. To make something a polar molecule, here's your requirements. Has to have at least a polar bond, right? How can it be a polar molecule, if it doesn't have a polar bond? With the exception, that lone pair on the central atom distorts the symmetry, even though you have nonpolar bonds, right? Put that aside. If you've got a polar bond, it qualifies as potentially a polar molecule. But remember, if it's symmetric, those polar bonds can cancel out in 3-dimensional space. But if it's not symmetric, those bond dipoles do not cancel out. Now, the atoms may be oriented symmetrically. We're not interested in that. We're interested, is the electron charge, is the electron density symmetric? So you might have atoms oriented symmetrically, but if those atoms are different elements with different electronegativity values, the electron distribution might not be symmetrically oriented. So it's really important. That's why you look at the bond polarities. If the bond polarities cancel, yes, that would be nonpolar. But if they don't cancel, it would make it polar because you'd have more electrons on one side than the other. A way you can look at that is vector mechanics. If you've ever done vector mechanics, probably in physics or maybe high-level mathematics, that helps a little bit. It's looking at, arrows pointing in 3 dimensions. We can sort of look at it. I'll play with it a little bit, but if you don't like it, don't worry about it. I don't think it's necessary for this class, but it can help, right? So let's look at some examples. I did some work for you ahead of time because we've already done Lewis structures, Wesser structures, and bond polarities. So you can double check my work if you want. But is carbon dioxide polar or nonpolar? It's your prototypical first example. When you usually this and then water, almost always, because it really nails the point because they look similar. Their Lewis structures look similar, but their polarities are totally different. So if you do your 6n plus 2, you end up with a positive 4, which means we have 2 multiple bonds. Do the Lewis structure, you get the 2 double bonds. We could have done a triple bond on one side for resonance and whatnot, but this is the dominant structure. And look, nice and linear. And if we do the Wesser structure, that carbon has 2 electron groups, both are bonding, so it's going to be linear either case. Now, when you're doing this, you don't need to label the linear, square pyramid, that kind of stuff. I just want to see how it's arranged in 3-dimensional space. You don't need to include the lone pairs on the terminal atoms, but I would include lone pairs on central atoms so you can see it if it distorts the symmetry. So that's what it looks like. Looks pretty symmetric, would you agree? Now let's do the bond polarities. Now, both bonds are carbon-oxygen double bonds, so we only have to do the calculation once. Each bond would be the delta En. So if you look on your electronegativity table for carbon, remember this? You're going to need this. So carbon is 2.55, oxygen is 3.44. So you subtract those and take the absolute value. You end up with 0.89. Well, that's greater than 0.4, but less than 1.7, so that's a polar covalent bond. So that satisfies the first thing on the checklist for polar molecules. It has to have at least 1 polar bond. Hey, this has 2 polar. All the bonds are polar. Yay! So you'd think this is going to be polar. No. There's another factor. You have to look at how those polar bonds are arranged in 3-dimensional space. What's the symmetry? Notice that this is perfectly symmetric, right? This is symmetric. This is a symmetric structure because it's atomically symmetric and the electron distribution is symmetric because the bond dipoles are the same on both sides. So if we look at it this way, would you agree that there's oxygen's more electronegative? So if we did the bond polarities, it would be 0.89. That would be the delta En. It'd be better if we had the dipole moment, which is a factor of the partial charge and the distance, but we're not going to calculate dipole moments at this point. We'll just use the delta En, keep it simple. So that would mean we would have a dipole moment going that direction of 0.89, right? Well, what about the other bond? Well, that would be a dipole moment going that direction of 0.89. So in vector mechanics, if you add those two together, so essentially, you can see they cancel out here, but in vector mechanics, I'll do this and then I'll erase it. You start with the first, so let's say this is the first bond and the second bond. So the first bond, right, you go that direction, and then what you do for the second bond, you take the tail of that one and add it to the head of that one. So you go right back, exactly 0.89, and you end up where you started. If you do all the bond dipoles with the vector, which means the length of the arrow is based on the delta En, oversimplification, and it's pointing in the correct direction in 3-dimensional space, and then you do it each bond in turn, so bond, start with bond, whatever bond you want, start with bond number 1, bloop, from the center of the molecule, boink. Then do bond number 2, then bond number 3 in the proper direction in 3 dimensions with the proper length, right? The more polar it is, the longer it is. And if you end up where you started, that'd be a nonpolar molecule. If you end up somewhere else, you take where you started and where you ended and draw that arrow. That's the overall molecular dipole moment. Oh, it's called vector mechanics. If that didn't make any sense to you, don't worry about it. You can see that those cancel out, right? So if I'm doing a lecture, I'll have two students come up, big burly people, real strong people, and they dislocate my shoulder or something. And I'll stand there like I'm carbon, and I'll form the carbon-oxygen bond here to one person, and I'll form another carbon-oxygen bond to the other person. I'll have them on opposite sides and say, pull. And if they pull with the same strength, I don't go anywhere, do I? It cancels out. But if they pull with a different strength, if those were different electronegativities, values, if that was like a 0.6 on this side would be pulling more, and I would go over this way. I would no longer be nonpolar because it would be an asymmetric electron charge distribution. So if that was a different atom, if that was sulfur or something, so say this was sulfur, the oxygen would pull more, and you'd have an overall arrow pulling you this direction. So where that central atom goes is the dipole moment of the overall molecule. Oversimplification. Vector mechanics is the best way to do it. But you can see these cancel out, right? So because those cancel out, so the bond dipoles cancel. So here's how we can phrase this answer. This is how I like to see it when you're answering a question. Okay, so let me erase all this. Those bond dipoles cancel out. So if I want to answer this question, let's state the fact. Is CO2 a polar or non-polar molecule? It is a non-polar molecule because it has polar bonds, but it's symmetric and they cancel out. So let's say CO2 is a non-polar molecule. There's the answer, and I'll usually ask you to explain why. Because it is symmetric. Ooh, I felt my shoulder start popping out there. And the bond dipoles cancel. Because it's got polar bonds, but they cancel out. That is how I would answer that question. Right? You proved it has polar bonds. You proved it's symmetric. Therefore, they cancel out. So CO2 is a non-polar molecule. Wada bing, wada boom. Let's do water, your prototypical polar molecule, even though it won't look like it from the Lewis structure. Don't use the Lewis structure to look at symmetry. Use the Vesper structure. All right, hopefully you did water ahead of time. Right, so take your 6n plus 2 minus number of valence electrons. 8 minus 8 is 0. We've done this before. It's all single bonds. Don't have to worry about expanded octets, all that fun stuff. So there's your Lewis structure. Now looking at the Lewis structure, that looks like carbon dioxide. It's just you have single bonds instead of double bonds. And it looks symmetric, doesn't it? So you would anticipate if you stop there, you would say, hey, water would be like CO2 because it's symmetric. The bonds are the same. They'd cancel out. This should be a nonpolar molecule. Wrong. You have to look at the Vesper structure in 3 dimensions. It's not linear. It's bent. Huge difference. Remember, you've got 1, 2, 3, 4 electron groups. 2 are bonding, 2 are non-bonding. That gives you a tetrahedral arrangement. And I put the lone pairs on the dash and the wedge. So let me simplify this. Look, let's get rid of the dash and the wedge. And just draw the lone pairs there. Which technically you don't need to in the Vesper structure, but it just lets me know. So see how that distorts it? That's no longer symmetric in 3-dimensional space as far as the electron distribution. Those hydrogens are not on opposite sides. Those bond dipoles don't cancel out. They are going to enhance each other. Whoop, 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 whoop. Makes a big difference. Let's calculate the bond polarities. So both bonds are oxygen, hydrogen. So if you look on your electronegativity chart, right, hydrogen's a big 2.2. Oxygen's a 3.44. So if you subtract those, I get a 1.24. That's good to 1 decimal. Doesn't make a difference, but technically we're limited to 1 decimal place. I need that hydrogen to 2 decimal places. So that's definitely, now that's more polar than the CO bonds, the carbon-oxygen bonds of CO2. So this has much more polar bonds. If you look at the Lewis structure, you'd say it's a non-symmetric molecule. But if you look at the Vesper structure, it's not. It's an asymmetric species. So those bond dipoles are not going to cancel out. This is going to be a very highly polar molecule. So let's take a look at the bond dipoles. If you follow vector mechanics, right, this is asymmetric. Let's say this is bond number 1 and bond number 2, right? So it has a value of 1.24. So, and it's more electronegative towards the oxygen, right? So let's do this. So let's take bond number 1. So let's do vector mechanics. You ready? So bond number 1 will point towards the oxygen. So it's going this way, blah, 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 with a value of 1.24. Right? So this is bond number 1. Now let's take the tail of bond number 2 and start that on the arrow of this. So it points back. Now this is flat. That's why I put the lone pairs on the dash and wedge. So this is a planar molecule. Right? Nice and simple. See how that's planar? Boop, 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 boop. So now what I'll do is I'll start bond 2 here and go with a 1.24 back this direction. See how it's at an angle? This goes straight down, but that's at an angle, so it goes whack. So this is bond number 2 with a 1.24. So here's where I start. Oh, fumbled my purple pen. So here's my start. Did I finish where I started like I did for CO2? It did not, did I? So what that means is you start here and end here. Boop. You see, that's your overall molecular dipole moment. Let me draw it on this molecule. You ready? So I'm going to draw water all over again, but it's going this direction towards the oxygen. Do you see that? So you're going to have a partially negative region by the hydrogens and a partially positive by the hydrogens and partially negative by the oxygen. So let me draw this over again. And if the vector mechanics didn't make sense to you, again, you don't need to worry about it, but it really gives you a nice answer. That's what the computers can do really easily. So would you agree oxygen's more electronegative than hydrogen, right? That means it's pulling electrons this direction, so you're going to build up a partial negative charge here, and the center area of the hydrogens, you'll build up a partial positive, right? So here's the oxygen. I like to put holes for lone pairs. So you're building up a partial negative charge here and a partial positive charge there, and you just draw an arrow, shunk, right from the positive to the negative, which is where... Remember when we did from the beginning to the end in the vector mechanics? That's your dipole. That's your molecular dipole moment. And a computer software could calculate that mu symbol. Could calculate that in, I think it's dBs or something like that. Again, it's the partial charge and the distance, all that kind of stuff. But they use a unit called a dBi to measure the dipole moment strength. So this is a very polar molecule with more electron charge on this side, less on this side. But you really, instead of vector mechanics, you can just say, well, the oxygen's pulling, it's more electronegative, so it's pulling electrons from the hydrogens, so it's building up electrons here and losing electrons here. There's more electron density on this side and less on that side. So I would say water is a polar molecule. Remember, when you say polar or nonpolar, tell me, is it a polar bond or a polar molecule? Is a polar molecule, boom, because it has polar bonds, right? Remember requirement number 1, and is asymmetric. What does that mean? Bond dipoles don't cancel. So the bond dipoles don't cancel. That would be a very, very detailed answer. Instead of just saying it's a polar molecule. Well, why? Okay, well, you proved you have polar bonds, right? And we proved it's asymmetric to the Vesper structure. And if it's polar, I want you to draw the dipole, the molecular dipole moment. Boop! We're not going to calculate it, but I want you to qualitatively show me, pointing from the side with less electron density, partial positive, to the side of the molecule with more electron density, partial negative. Ho ho! Let's do a more complicated molecule. Try CH2F2. Now, ideally, don't look. Pause and do it and see what you get. And then look. Right. So if you do 6n plus 2 minus valence electrons, you get a value of 0, all single bonds. Okay. Lewis structure, all single bonds, complete the octets on the fluorines. Looks fairly symmetric, right? Don't look at the Lewis structure for symmetry. Look at the Vesper structure. So we got a tetrahedron because we got 4 electron groups. Doesn't matter where you put the fluorines and hydrogens. Doesn't matter. But I do like to put the 2 fluorines next to each other rather than across like that. It's easier to see. I like to place the atoms so I can see symmetry or asymmetry a little bit easier. So I can see those fluorines are not opposite each other, right? So if I do the model for this, imagine the blue is fluorine and the white is hydrogen and the black is the carbon. You can see the tetrahedron. So I orient it like this. So here's the carbon with the fluorine, and those are in the same plane. And then you got a hydrogen coming at your face right there. That's the open wedge. And the hydrogen coming towards my face right here. That's the dash wedge. Okay, so the atoms are symmetrically oriented, but that's not what symmetry means. Symmetry is the electron density, not the atoms. Notice the fluorine's more electronegative than the hydrogen. Can you see these fluorines are going to be pulling electrons from the carbon? Carbon's going to pull electrons from hydrogen. Let's look at the bond polarities. If you can't see that, look at the bond polarities. Now we've got 2 types of bonds, carbon-fluorine bonds and carbon-hydrogen. We have 2 carbon-fluorine single bonds and 2 carbon-hydrogen single bonds. So let's do the carbon-fluorine bonds and the carbon-hydrogen bonds. Look on your electronegativity table. Carbon, of course, is 2.55. Fluorine is a 3.98. Hydrogen's a 2.2. Okay, so if you take carbon minus fluorine, you get a 1.43. Those are polar bonds. Oh, it could be a polar molecule. Carbon hydrogen is 0.35. That's less than 0.4, so those are non-polar bonds. Doesn't matter. We have polar bonds, so this could be a polar molecule if it's asymmetric. That is asymmetric. Why is that asymmetric? Okay. The fluorines are pulling electrons from the carbon. You agree? But the carbon's pulling electrons. Carbon's more electronegative than hydrogen. So carbon is pulling electrons from the hydrogen. Do you see how they're all moving this direction? So you're going to get less electron density here as it pulls towards the carbon and out towards the fluorines. Where's the average area between the fluorines? Right about here. So you're going to build up a negative charge right there. I don't like having all those arrows for each bond because you confuse that with the overall arrow for the dipole moment of the molecule. And then you're going to get a partial positive down here in between the 2 hydrogens. See that? So you have this overall drive of electrons towards the fluorines. So you get this molecular dipole moment heading towards the fluorines. So you look at the symmetry of the structure and you go, oh, ka-chunk. Even though it's 3-dimensional, it's coming right between these 2 fluorines, shish kebabbing the carbon, starting between the hydrogens. So if I take a pen and go shloop, and then shloop, right through like that, you can see it. If I can't skewer through the carbon with my pen, break my pen, but you get a polar molecule. It's an asymmetric electron charge distribution. So I would say CH2F2 is a polar molecule, right? And always draw the dipole moment if it's a polar molecule, right? Because just like water, it has polar bonds and is asymmetric. Or you could say is not symmetric. I don't have room, but I would say, bond dipoles do not cancel. That changes a lot about its properties. Now, what if all 4 of those were fluorines? Then it would be perfectly symmetric in 3 dimensions. Yes, you would have 4 polar bonds, but they would all cancel out. If you did vector mechanics, it's hard to do vector mechanics in 3 dimensions. You have this way, this way, this way. You would end up where you started, right? So this would be a non-polar molecule, CF4, right? Even though it has highly polar bonds, that would cancel out. Let's look at one complex molecule with multiple central atoms and show you how to think of it overall. This last one will be a fun one. You ready? Let's do CH3, CH2, NH2. Oh, Is that polar or nonpolar? So we got a complex molecule now, 2 or more central atoms. So if you do the 6n plus 2 minus valence electrons, it's the same as we had for the last one we did. You get 20 minus 20, 0. We got all single bonds here. So if you do the Lewis structure, you got 3 hydrogens on that carbon, 2 hydrogens on that carbon, 2 hydrogens on that nitrogen. We're going to need to draw the Vesper structure for this, but we got 4 kinds of bonds. We got carbon-hydrogen bonds, carbon-carbon bonds, carbon-nitrogen bonds, and nitrogen-hydrogen bonds. Doesn't matter if they're single, double, or triple. That's irrelevant. So we got 4 delta N's in here. Well, obviously, carbon-carbon, you're taking the same number minus itself. It's going to be 0, right? So carbon being 2.55 right there. So that's obviously nonpolar covalent bonds. Well, carbon-hydrogen, right? So carbon being 2.55, hydrogen being 2.2. You're going to get 0.35, which is less than 0.4. So those are nonpolar. So it's all nonpolar on this side. Now, let's look at the carbon-nitrogen bond. All right. Well, carbon's a 2.55. All right. Nitrogen is a 3.04. So if you subtract those, you get 0.49. That's barely polar. That's a polar covalent bond, but that's the weenie. It's weeniest of weenie polar covalent bonds. Let's look at nitrogen-hydrogen. Okay, so hydrogen's a 2.2, nitrogen's a 3.04. You get a 0.84. That's more polar. So these are both polar bonds, but this is more polar. You see the nitrogen's the highly electronegative atom there? The electrons are going to be moving towards it. I don't have a lot of room here, so I'm going to pause this, erase it, draw the Vesper structure for me, and see if you can see if that's symmetric or asymmetric. We've got polar bonds, but we got to look at symmetry and see if this is a polar molecule or not. Do it. How's your Vesper structure looking? Remember, this first carbon, that's your first central atom, has 4 bonds. All are bonding groups. So you draw the tetrahedron. So that would be tetrahedral. Second carbon also has 4 single bonds. So see the distorted tetrahedron, because that's bonds already written there. So remember, look at the Vesper structures for complex molecules if you're having trouble. So I just take my tetrahedron and go ding, kind of move it. So we got the 2 hydrogens on the dash and wedge, and that bond coming out goes to the nitrogen. Nitrogen has 3 single bonds and a lone pair. That's 4 electron groups. So we get the tetrahedral arrangement. That's the electron group geometry. But only 3 are bonding and 1's non-bonding. See the lone pair there? So what I'm going to do is I'm going to erase that line and just stick the lone pair there. You see how that's asymmetric now? That lone pair pushes those hydrogens together. Now, carbon's more electronegative than hydrogen, so it's pulling the electrons here, but nothing going on between the carbons. The nitrogen's pulling the electrons. So you can see how the electrons are going towards this side of the molecule. It's busted up, it's symmetry. So you're building up a negative charge towards the nitrogen over here. Okay? Which means the electrons are moving away from it. So on the other side, kind of over in this area, you're building up you're losing electron density, so it's partially positive, less electron density here, more electron density here. So just sort of generically, imagine that's an actual straight line. You get a molecular dipole moment cutting through. Yeah, good luck drawing all the individual bond dipoles in there. So I would say, what is this? Ethylamine, CH3, CH2, NH2. Remember, anytime you see that NH2 group, if you review the organic molecules, that's an amine. Those are polar, right? Typically very polar, very high soluble. We'll find out when we look at the effect on intermolecular forces. These tend to be highly soluble. So this is a polar molecule, because it has polar bonds, right? That nitrogen, hydrogen, carbon, nitrogen, those are polar, although carbon, nitrogen is barely polar. And is not symmetric. They do not cancel out in 3 dimensions, right? Bond dipoles don't cancel. So you don't really need the vector mechanics. You can just kind of see it's asymmetric. More electronegative atoms on that side. Boom! We got it! We're done with this whole section. Yay!